Have you ever wondered about the origins of Mars, its climate, the depths of its ancient seas, and what went wrong? Get comfortable, friends, because in the next 15 minutes, we'll dive deep into the intriguing history of the red planet. Mars's history dates back 4.5 billion years. While exact dates are elusive, we know that Mars formed slightly faster than Earth, partly due to its smaller size. Imagine a small ball gathering matter from a protoplanetary disk quicker than a larger one. Mars became a finished planet just 10 to 20 million years after the solar system formed. Meanwhile, Earth and Venus continued to accumulate material for several tens of millions of years. While Mars is the last of the inner planets, the oldest planet is actually Jupiter, an outer planet. Inner planets like Mars formed under stronger solar gravity with heavy materials like iron and silicon. Outer planets, formed further from the Sun, are mostly made of gas and ice due to weaker solar gravity and an abundance of lighter materials. Jupiter's formation influenced the entire solar system. Its immense gravity affected the orbits of other planets and debris, playing a significant role in shaping the solar system's structure. This gravitational pull also likely influenced Mars's development, potentially limiting the amount of material available for Mars to gather during its formation. We know about Mars' ancient age from meteorites that have journeyed from Mars to Earth. For instance, the analysis of zircon in one meteorite revealed an age of 4,547,000,000 years, only 20 million years after planet formation began. These meteorites, often ejected from Mars by asteroid impacts, provide valuable insights into the planet's early history. Why did Mars stop developing and never reach Earth's size? Many scientists blame Jupiter's gravitational influence for diverting extra material away from Mars. Additionally, Mars's smaller size and mass meant it cooled more rapidly than Earth, halting its geological activity sooner and preventing the sustained accumulation of material. Mars' history is traditionally divided into 4 periods: Pre-Noachian, Noachian, Hesperian, and Amazonian. Pre-Noachian period. This period followed Mars's formation. Unfortunately, we know little about it because the oldest visible surface areas date back only about 3,800,000,000 years, marked by numerous craters. Mars, like Earth, experienced significant collisions, including a possible impact with a large asteroid or dwarf planet, leading to an abnormally high concentration of heavy elements in its mantle. Mars's appearance today is partially due to its violent past. The northern hemisphere is almost perfectly flat and young, while the southern hemisphere is old, tall, and covered in craters. This dichotomy is partly due to a massive impact in the planet's early history, which may have also led to the formation of its moons, Noachian period, and Deimos. Beginning 4,100,000,000 years ago, Mars became habitable. It had a hot ocean, dense atmosphere, and suitable temperatures. Volcanic activity was rampant, creating a greenhouse effect that warmed the planet. This period saw the formation of many basins, rivers, and lakes, such as the former Neretva River and Lake Ezeru, where the Perseverance rover found traces of water. The bombardment of meteorites continued during this period, though on a smaller scale. This period was crucial for the development of potential life. The presence of liquid water, a thick atmosphere, and a magnetic field created conditions similar to those on early Earth. If life ever existed on Mars, the Noachian period would have been the most likely time for it to thrive. Hesperian period. The Hesperian period began 3,700,000,000 years ago. Mars lost its magnetic field, volcanic activity diminished, and the planet cooled. This era was marked by significant flooding, reshaping the landscape. Despite these changes, Mars still had a substantial hydrosphere, including the northern plain, which housed a salty ocean up to a kilometer deep. The Valles Marineris, a system of canyons that runs along the equator of Mars, is one of the most striking features from this era. These canyons are up to 7 kilometers deep and over 4,000 kilometers long, dwarfing Earth's Grand Canyon. The Hesperian period also saw the formation of Olympus Mons, the solar system's largest volcano, which stands so tall that it creates a vacuum at its summit. Interestingly, Olympus Mons last erupted only 2 million years ago, suggesting Mars is not entirely geologically dead. Amazonian period. The Amazonian period began about 2,900,000,000 years ago and continues today. Traditionally seen as Mars's decline, recent studies suggest a more complex picture. Mars may have retained life-supporting conditions until relatively recently, and it's not entirely geologically inactive. The InSight mission detected over 500 quakes, indicating active geological processes. Moreover, Mars has a layered core with a liquid outer layer, a solid inner core. Recent observations suggest Mars might be emerging from an ice age into a warmer period. If all the ice melted, Mars could be covered by an ocean about 10 meters deep, and the solid carbon dioxide in its polar caps could create a thick atmosphere, potentially setting the stage for a greenhouse effect and global warming. Mars's potential to support life has intrigued scientists for decades. During the Noachian period, Mars had conditions similar to early Earth, with a thick atmosphere, warm temperatures, and liquid water. This has led to speculation that life may have arisen on Mars during this time. The discovery of organic molecules by the Curiosity rover and the detection of methane in the Martian atmosphere further fuel the possibility of life. Methane can be produced by both geological and biological processes, and its presence on Mars suggests that the planet may still be geologically active or that microbial life exists. In addition to methane, the detection of seasonal variations in the amount of methane in the atmosphere is intriguing. This variation could be a sign of biological activity, though it could also result from geological processes. Future missions will aim to determine the source of this methane and whether it indicates the presence of life. Today, Mars is a cold, dry, and barren world, but it remains a focus of scientific exploration. Rovers like Curiosity and Perseverance continue to study the planet's surface, searching for signs of past or present life. The Perseverance rover, in particular, is exploring the Jezero crater, a former lakebed that may hold clues to Mars's watery past. Future missions aim to bring Martian samples back to Earth for detailed analysis. These samples could provide definitive answers about the planet's history and its potential to support life. NASA's Mars Sample Return mission, in collaboration with the European Space Agency, plans to collect and return samples by the early 2030s. Additionally, plans for human missions to Mars are underway. NASA's Artemis program aims to return humans to the Moon by 2024 as a stepping stone for future Mars missions. Private companies like SpaceX, led by Elon Musk, are also developing technologies to enable human settlement on Mars. Elon Musk's vision of terraforming Mars involves creating a livable environment for humans by warming the planet. This could involve releasing greenhouse gases to thicken the atmosphere and raise temperatures. While this idea is still theoretical, it highlights the potential for Mars to become a second home for humanity. Colonizing Mars presents numerous challenges, but also exciting opportunities. One major challenge is the planet's thin atmosphere, which provides little protection from harmful solar radiation. Future settlers will need to live in shielded habitats or underground to avoid radiation exposure. Mars's low gravity, about 38% of Earth's, could also pose health risks to humans over long periods. Prolonged exposure to low gravity can lead to muscle atrophy and bone loss. Scientists are researching ways to mitigate these effects, such as through exercise routines or artificial gravity habitats. Another challenge is the lack of liquid water on the surface. While there is ice, extracting and melting it for use will require significant energy. However, if successful, it could provide water for drinking, growing food, and producing oxygen through electrolysis. Despite these challenges, the opportunities for scientific discovery and human expansion are immense. Colonizing Mars could provide a backup location for humanity in case of a catastrophic event on Earth. It could also drive technological advancements that benefit life on Earth, such as new methods for sustainable living and resource extraction. While the search for past life on Mars is ongoing, scientists are also interested in the possibility of extant life, life that exists today. If microbial life exists on Mars, it is likely to be found in subsurface environments where liquid water might persist. Mars has surprised us many times, and who knows what the future holds. Maybe the red planet will warm up and become habitable again. Share your predictions in the comments. Thanks for watching, and don't forget to like, subscribe, and hit the bell icon for more exciting space stories.